Hello, Algebra. Welcome to Lesson 6.1, Congruence and Reflections. Like I mentioned yesterday, we are about to start a chapter that will require graph paper. So you want the ones that are divided into little segments of 5 each. Okay, so let's begin with the term congruent or congruence. Here we go. Congruent basically means equal. So two figures will be congruent if all corresponding sides are equal, all corresponding angles are equal, and if that happens, they will fit exactly when one is placed on top of the other. Congruent figures, you should keep in mind, may have different orientations. For example, they might have been slided, flipped, or turned. Here I have an example of what congruent means. I have two triangles. Now, I sketched them. They do not visually look congruent. They do not visually look exactly the same. And you keep this in mind also when you are looking at things that are printed in a book. What you have to sometimes rely on are the markings. So here I have triangle ABC, and here I have triangle PQR. Notice first of all the sides. AB is the same as PQ, indicated by the single tick mark. AC is the same as PR, which is indicated by the triple tick mark, even though I kind of did a little divot there at the top. BC and QR are the same because of the double tick mark. So the three sides are the same. The next thing to check are the angles. So the angles A and P are the same with the single curve. B and Q are the same with the double curve, and C and R are the same with the three curves. Therefore, these two triangles are congruent. Since they're orientated the exact same way, it is quite easy to find that out. So if you would please look at example, not try it, but example 1 on page 131. Look right at the top there, and I'm going to just slide my book here, which is hard because I use my book as a weight to, I'm going to see, yeah, okay, this is good enough. So it's a little at an angle, but I can't get it straight under my thing. So anyway, they say determine whether the following pairs are congruent. Well, if you look at these two triangles, they're basically flipped. So they each have a right angle at B on the left and D on the right. And we have, if we flipped them over and matched them, the solution would say you would have the same exact figure. So the sides measure the same, the diagonals measure the same, and the bases measure the same. So if you flip them over, they would fit exactly, therefore they're congruent. In B, if you would draw the quadrilateral TXYZ on a sheet of transparency paper or on a paper and just keep rotating it, you would find that this also fits right on top of SRQP because TZ fits there, so it would fit. However, with these two circles, circle O is definitely smaller than circle G. They would not fit on top of each other, so those two would not be congruent. Okay, now let's go to try it 1, and I have to shift my book off now and turn a page. Okay, like I said, this is going to be something different than we're used to. But if you go to page 132, we're going to work through what we see on these pages. So try it 1. If you look at the two triangles in A, we would say that they are congruent because of this. what I did is I reconfigured the second triangle and I reorientated to mirror or mimic the first one. And looking at that, I find I have a right angle E, which corresponds with right angle A in the first one. And then the sides are the exact same measurements. So EF is like AB in that they're both 4. ED is the same as AC, which is 3. And then, of course, the bases are also the same, which are 5. Therefore, they're congruent. Now, here's one way of writing that. So this symbol right here means congruent. So I would say ABC, which is the first triangle, is congruent to triangle EFD. I left off the triangle sign probably because I had the therefore and just simply forgot it. I should have included it to be complete. Now, if we look at B, we see a rectangle and then we see a parallelogram. I can't call the second figure a rectangle because it's slanting. Therefore, the angles of the parallelogram PQRS are not right angles. And so therefore rectangle KLMN and parallelogram PQRS are not congruent because the angles don't match up. If you look at the quarter circles in letter C, each quarter circle, I should have had has, my goodness, mistakes one after another. Each quarter circle has an equal radii. So they both have the same radii of 4, therefore they are congruent. Because in order to be a congruent circle, you have to have either the same diameter or the same radius. So I am going to correct my mistake here, and I'm going to throw a triangle in up there. Okay, there we go. My apologies. Now let's move on to reflections. These are a little trickier. A reflection basically is a flip of an object over a line of reflection. And that line of reflection is called either the axis of reflection, the axis of symmetry, or simply the mirror line. Now, we've done axis of symmetry before in level 6, I believe in level 5 also. So this is a review, but there's some little more advancements in this book that will help us do this more mathematically than just visually, which is always a little trick to do it visually. Reflections are a little tricky. However, here are the rules. In a reflection, the original object and the image, so the image would be the reflection, the original object and the image are congruent, so they're exactly the same. Any point A and its image, which we would say A with a tick mark, are equidistant or equal spaces apart from the line of reflection. The line of reflection is the perpendicular bisector of the segment joining every point and its image. I'll illustrate that in a moment. And the orientation of the object and that of the image are different. So the orientation is always different in a reflection because it's usually flipped. Okay, now right here I say go to page 134 and look at that diagram with the steps. This one I think I don't have to make slanty. Let's go like this. Here we go. So if you look at this, what they did is they took the original triangle here, ABC, and they had them on those points, and they reflected it over the y-axis, okay? And what they did is they went through those steps, and that perpendicular thing is what I want to talk about. So the first thing is draw perpendicular AF from A to the y-axis. So basically what we're, oops, I am so sorry. I got to get something to anchor this. Well, isn't this going to be an interesting little ride here? What can I anchor it with when I don't have my book? Ah, my bag. Okay, you're right with you. There we go. Okay, all's well. All is well. All is well. That's a Michael W. Smith song. Okay, anyway, I digress. So here we go. So this is drawn. We're supposed to reflect it over the y-axis. So we got to go this way. So here's that perpendicular. I go from A, and perpendicular just means draw it straight on over to hit that y-axis. And you designate perpendicular with this right angle thing. And then what you do is you produce a point that is the mirror image of this first point. This is a whole block of steps, so 5 little boxes from that perpendicular. Keeping on that perpendicular line, I go 5 more this way, and that is my new point of reflection for A with the tick mark. So that's my image. This is my original, this is my image. Each are 5 little spaces away from my y-axis. I do the same with all the other points. This point happens to be 15 spaces away from there, 15 little spaces or 3 big chunks away. So keeping that perpendicular line going across from point B, I go 3 big spaces here, and there's my image B at 3, negative 3. It's not negative 3. Yeah, it is. Negative 3, 2. So here, this is negative 1, 4. Here, it's just 1, 4. Here, it's 3, 2. Here, it's negative 3, 2. Now, point C is at 2, 1. So another perpendicular line. It's 2 big spaces or 10 little ones this way. I go the same direction this way, and I'm at negative 2, 1 right here. And then I connect my dots, and I have a reflection. So this is the original. X is the line of symmetry, or the line of reflection. And I have the mirror image right here, or what they call just the plane image, or the reflection is there. So that perpendicular business is just making sure that these are exactly straight across from each other. And that's all it is, basically. So let's go on now to the next point. And let's see. Some generalizations now about reflections. These are rather important. The image of the point, which could be AB, under a reflection in the y-axis. So if we're told to reflect it over the y-axis, would be negative AB. So we're going to be working with positives and negatives. The rules apply, and I'll show you how nifty that works out in a moment. The image of the point AB under a reflection in the x-axis is just the opposite. It is point A negative B. Keeping all that in mind, there's one more point, I believe, to consider, and that is number 3. Points on the line of reflection. So if the point actually ends up on the y-axis or the x-axis, remain unchanged under a reflection. So if they're on that point of reflection, they don't change. They don't change. And such points are called invariant points. Doesn't happen too often, but sometimes it does. So in try it number 2, which is at the top of page 137, we have a set of points. P is at negative 4, 0. Q is at 4, negative 1. R is at 1, 0. And S is at negative 2, 3. So I would make my graph. And if you can kind of see, I have kind of a dotted graph on here. So I just quickly sketched it. And I placed these solid points without any tick marks on my line. So for example, negative 4, 0 is here. That's my P. 4, negative 1 is my Q. 1, 0 is right on the line. That's my R. And -2, -3 is my S. Now, what I did to find out the reflection, which is letter A, their image is PQRS with 1 tick mark. The first reflection is obtained under a reflection of the y-axis, which is -AB. Now, what you do is you take your original coordinate point, -4, 0. Well, if this is a negative and a negative, that's going to turn that 4 positive. This is a positive and 0, 0 just always stays the same. So I have 4, 0. Now doing the same for the other points on the y-axis, a negative and a positive make a negative, and a positive and a negative make a negative. So I have -4, -1. So I'm just going to put a negative value with this coordinate part of the coordinate pair, and I'm going to put a positive value with this, and I'm going to kind of multiply and see what happens. So here I have 1, 0. Well, if I'm going to put a negative with that +1, it becomes -1. If I put a positive with 0, nothing happens to that 0. It's just 0. With the S, I have a negative with a -2. So a negative and a negative turn that into +2. And then I have a positive and a negative, and that stays a -3. So with these negatives and positives, it's like multiplying by a -1 for the A's and by a +1 for the B's. Now, moving to the x-axis, I'm going to do the same thing. I'm going to go back to those original ones. I'm all done with these. I'm going to go back to the original one and apply this. So I have a -4 times a +1. That would be a -4. And then a negative b times 0, just 0. Because 0 times anything is 0. With q, I have a positive and a positive here. So that stays 4. And a negative and a -1. That also turns positive, so it's 4, 1. Here I have a positive and a positive, which is a +1, and then another 0, which is 0. And then a positive and a negative leaves that -2. Here's a negative and a -3. That turns that 3 positive. And then I have those points. I like to figure out my points using the generalizations, because then putting them here is real easy on one graph, and I don't have to do all that counting and drawing the lines. You can draw the perpendicular line and do all the counting if you'd like, but I find I make more mistakes that way. So basically then I go to 4, 0 right here, and that's where I put my first reflection of P, and then -4, -1, that is my, or -4, -1 rather, is my first reflection of Q, and then -1, 0 is my first reflection of R, and 2, -3 is my first reflection of S. Then I do my second reflections, and my second reflection of P is at -4, 0, which is at the same place as my original, so I just put P with my second reflection here. And then Q will be at 4, 1, my second reflection. So 4, 1 is right there. So I kind of had to stick that up there. Excuse me, 4, 1 is right here at that dot. And then the second reflection of R is at 1, 0, same spot. The second reflection of S is at -2, 3, way up there. So there I've done the math to actually figure out my reflections. And then once they're figured out, I just plot them on the graph. Now your graph paper will have more room because each of these distance will have those 5 little marks. It'll look much nicer when you do it, when you need to graph. Okay, Stop and pause this at any time. I think this right here is the thing that you will need to keep your wits about you. But if you remember those little formulas there, it's always easy to figure out the points and then do the reflection, which I find much easier than drawing the perpendicular line and counting spaces, which you can do, but keep in mind mistakes happen pretty easily with that method. Okay, your assignment for tomorrow is to do pages 137 and 138, numbers 1 through 4. You will have some that just deal with congruency, and you kind of have to eyeball those. Those are pretty much drawn to scale. Number 2 on page 138 also has additional markings to help you determine the pairs that are congruent with one another. Then for 3 and 4, you're going to need to do those problems on graph paper, and you're going to need to do some reflections. So just keep this in mind for the reflections. With the graph paper, you would just insert that into your notebook. So you can do 1 and 2 right in your notebook, and then insert 3 and 4 into your math notebook to do. And just keep it all together for grading purposes. If you have any questions, please ask. And remember, you can rewatch this as often as you need to. You can pause, rewind, copy all the information down, particularly study this. I can't emphasize that enough. And when you do the graphing, be exact. There is no space for incorrect graphing. As Pastor mentioned to me, the space probe to Mars never made it, and it's just floating out there because they were off a millimeter in their graphing. It makes a difference, particularly if you work for NASA. Okay, have a good day. Do good math.